Hello, in this video, we'll be talking about everything you need to know about topic 3.2, which is about modeling a gas, basically looking at the behavior of gases at the atomic scale. All right, so a big part of this is talking about what we call the kinetic model of an ideal gas. This is a mathematical model that we use to describe what is going on with a gas. It's a little bit of a simplified view and a statistical treatment. So we use statistics to explain what happens on the large scale when you have a gas in a container. It's going to be focused on like kinetic energy. So it is the idea that the macroscopic property like pressure or temperature can be described by thinking about what's going on with the movement of molecules. Here's a quick little animation to give you the idea of what we want to picture when we picture a gas. We talked about this a little bit when we looked at phase change. But the idea with the gas is the molecules of the substance have been pulled apart and increased their potential energy to a point where there are no more intermolecular forces. They are all bouncing around kinetically. So we can model this. We can say what happens if I have 100 little particles and they're all basically little ping pong balls bouncing around. We can look at a simulation for an example of this. This PhET simulation is a great example of the ideal gas law. It is a simulation you will use, and it is very much a model of kind of how gas particles will behave. So this is a computer simulation. They have put in the code to explain what will happen. I've put a few pumps from an air pump in, and now we have some gas molecules flying around. These little red dots represent individual molecules of the gas. And the computer simulation models them in a very simple way. It basically like codes these like they're just little ping pong balls bouncing around. They hit the wall, they'll bounce back. They've put a few things into the quote engine here. The idea is that all of these collisions are elastic. The little red balls only interact with each other when they bump into each other. There's no like push or pull from a distance. Those are the main things, but that gives us a really good picture of how a gas behaves. This computer simulation is a very, very good predictor of what will happen if I had like a container that had this pressure and this temperature. And it'll do things like it'll show us what happens if I say change the size of the container. Here we go. I can see that if I'm keeping the temperature constant, the pressure will change in a certain way. It'll also tell me what happens if I increase the temperature and heat things up. And I can see the pressure has some relationship there. So this is the idea with a model, something like the ideal gas model. It is a simplified way to kind of describe what's going on, and a good model will give us predictions that are very similar to what we see in the real world. So when we're thinking about an ideal gas, we're talking about a something you could model, something you could simulate with some basic rules, and we say if these basic rules are true about the system, this is how it should behave. So that's the idea with an ideal gas, and we'll get into some detail here in a minute, but there are certain conditions where an ideal gas will model a real gas, where a real gas will behave almost exactly like this. Even though it's a little more complicated, this is a really good way to look at it. So when we make our computer model, or when we want to talk about the rules that these little ping pong balls need to obey, we have a set of rules. We call them the assumptions of an ideal gas. An ideal gas is a gas that follows these rules. And again, the idea is many times real gases will behave in ways that match the predictions of the ideal gas model. So these are the rules for an ideal gas, the rules that go into, say, that computer simulation. You do need to memorize these. The IB is very fond of asking you to discuss some of the assumptions of an ideal gas model, or to say pick them out of a lineup when you're looking at a paper one question, something like that. So you want to commit these to memory. The first two are definitely the most important. So the first one here is we are assuming that the molecules undergo perfectly elastic collisions. So when they collide with each other, or when they collide with the walls of the container, they exert a force, there's a collision, there's an impulse, but there's no loss in energy, and so no like heat is generated by the collisions of these molecules. So we're assuming perfectly elastic collisions, so all of the kinetic energy is conserved. A big reason we call this the kinetic model of an ideal gas. We also assume there are no intermolecular forces between the molecules. So again, they're kind of bouncing around independent of each other like ping pong balls. When they get close to each other, we ignore any intermolecular forces that might occur. And we'll talk about basically when that's a good assumption. But since the molecules are moving around so quickly and there are really no more bonds that are there, and when there's a solid or a liquid, we are assuming there are no intermolecular forces. So again, the only forces come up between actual collisions. All right, there's a whole bunch of other assumptions that you also need to know. Those first two are definitely the most important. But here you go. We're assuming that they're in constant random motion and at relatively high speed. So they're constantly moving around. There is a good bit of kinetic energy in the molecules. We also need there to be a very large number of particles. This is because we are using statistics and we're taking statistical averages. We're doing things like assuming there are as many molecules moving to the right as there are moving to the left. And when you have a billion of a billion of a billion of molecules moving around, that's a very fair and safe assumption. But we need there to be a very large number of particles. These can either be molecules or like individual atoms. It depends on what kind of substance we're looking at. It doesn't really matter, but a very large number of identical particles. Of course, we assume they obey Newton's laws of motion. The idea is you could conceivably look at every single particle and plot its trajectory and like look at its momentum vector. And when it hits the particle next to it, you could do some momentum math and you could figure out what happens in the collision and then see where they go from there. And you could do that 100 billion times for every single particle. That would be very time intensive. The idea is the ideal gas law lets us not do any of that and just look at overall the process that's going on. We assume like under the hood, all of these particles are obeying Newton's laws of motion as they bump and smash into each other. We also need them to be small compared to the volume of the container. So we treat these as point particles. That would be our term that we use for this. They occupy essentially no space. They just exist at a point. And compared to the size of the container, they might as well have zero size. And again, that's a very fair assumption. They, are 0.00000000001% the size of the container or less. And we assume that they spend most of their time flying around. So the time that they are in a collision and bumping into something else is much less than the time that they spend actually moving in between collisions. And since collisions are so short, this is also a pretty fair assumption. All right, so that's the list of assumptions. Make sure you have them written down somewhere. This is the type of thing that you may want to make flashcards or a Quizlet or something. It's at some point, especially if you are, say, studying for the IB exams. There are a few different properties of a gas then that we'll look at, and we'll look at how they all relate. The first property is pressure, so we need to make sure we've defined pressure first. Pressure, the definition is simple. There is an equation in the data booklet. It is force per unit area. This is probably something you did long ago in science class. But this is the definition for pressure. It is a force exerted over an area divided by that area. We measure pressure in newtons per square meter, which we also have a fancy word for. That is a Pascal. So Pascal is a newton per square meter. But that's how we measure pressure. Force is part of it, but it's a exerting a force over an area. And here's a goofy picture of the idea of pressure. A nail is a good, very, very, very simple tool that uses this because a nail has a very small area of contact. You have a nice little point here, and so when you hit it with a certain force, well, the hammer will hopefully not go through the wall. A nail sure will, because it takes that same force and applies it over a very small area. And if I make this number small, the pressure is high. So pressure is what would puncture like a wall or something. If you were trying to do the same thing with a bowling pin, you would not have much success because the area of contact here is pretty big. It's the same force. You're hitting the wall with the same exact force. So force has nothing to do with whether or not the wall will be punctured. It's all about pressure. And the pressure Even though the force is the same, the pressure would be much higher here than it is here. So that's the idea with pressure. You know, snowshoes work in exactly the same way. You're walking out in very, powdery snow, you could easily sink down. Snowshoes are very big, so they distribute your weight over a larger area. The pressure is less, even though you're pushing down on the snow with the same force. The area on the ground that you're exerting that force over is bigger, and so you can walk over the snow. All right, on the microscopic scale, when we're talking about, say, balloons filled with gas and things like this, pressure comes from an overall force on the walls of the container, and that comes from the billions and billions and billions of collisions that are happening with the walls of the container every second. So it's kind of amazing, but you have to picture if a balloon is inflated, the thing keeping the balloon inflated is all these little tiny, tiny, tiny ping pong balls of air inside of the balloon that are punching against the inside of it. And there's so many of them moving at high speeds that keeps the balloon inflated. So same idea, we can measure the total force exerted by all of the molecules at any one moment on the walls of the container, divide by the area of the container. That gives us the pressure of the gas. Again, because we're talking statistical averages and there's so many of them, when we average out all those microscopic forces, it really does turn out, and you'll see this when you play with a simulation, you get an effectively constant force, you get an effectively constant pressure if everything else is the same. Here's one more picture just for fun. The idea of a bed of nails also uses this idea of pressure. You can see you can even squish a balloon against a bed of nails, and since there's so many of them, even though they have those little points, there's a lot of them, so the force here is being spread out over a relatively big area. If there was just one nail, this would be a very different story for this happy balloon. Okay, so what you really want to know now about the ideal gas is, when does this really work? We've been saying that it's a pretty good predictor, and it is, but there are a couple sort of limitations. So another thing you need to commit to memory is the conditions where a real gas will approximate an ideal gas. So the math that we're going to talk about, which comes from the ideal gas law, works, and you can predict like what will happen when you inflate a balloon, as long as these two things are true. First, the pressure of the gas has to be relatively low, and second, the temperature has to be moderate. These things are there both to basically make sure that there are no intermolecular forces. We want low pressure because if there's high pressure, then the gas molecules get jammed closer together, and there's going to be more of an effect of when they're very close together at high pressure, there will be some small amount of intermolecular forces that show up as they get close, and depending on the substance, they can push and pull on each other to different degrees. So we need a low pressure, and that's a relative thing. And this is, again, going to be like a paper one thing usually, where they'll give you options like low pressure, medium pressure, high pressure. So you don't have to worry about knowing values for any of these. You just want to know, generally speaking, in a relative way. You want low pressure, and you want the temperature to be pretty moderate. You definitely don't want it to be cold, because then again, they'd be moving super slowly, and they might not be moving with enough speed to kind of overcome those intermolecular forces. So it's really all about the intermolecular forces being low, really low enough to be negligible. All right, let's also look at temperature. There's an equation in the data booklet that we looked at in a previous video that talks about temperature, the macroscopic property of temperature, and how it depends on the microscopic property of the kinetic energy of the molecules of the gas. So this was the equation we looked at. Let's fully define everything now. So kinetic energy is a measure of temperature, or it's usually better to say the temperature of a substance is a measure of its average kinetic energy of its particles. Okay, so the bar means mean. You may have seen this in math class. The bar over top is a way to represent mean or an average. So this is average kinetic energy of the molecules. Keep in mind, a single molecule does not have a temperature. That doesn't mean anything because temperature is a macroscopic or a big scale property that measures the average kinetic energy of all the particles that make it up. So on average, how quickly are these gas molecules flying around? That's going to inform the temperature. And you can see it's an equation, so they're not equal. They're proportional, but they're not equal. They're different things. Definitely remember kinetic energy and temperature have very different units. They're completely different types of quantities. They depend on each other. But temperature is measured in Kelvin. Kinetic energy is measured in joule. And this is like a 3-part equation, so you can see you have a couple options of how to do this. Basically, they're related by, turns out there's a 3/2 out front, and then there's a constant here, K sub B, called Boltzmann's constant. It's in the front of your data booklet, times temperature. So that's one way to do it. And the other way is this. You might notice Boltzmann's constant is just a combination of what we call the ideal gas constant, or sometimes just the gas constant, or you might sometimes see the molar gas constant. But in the front of your data booklet, it's called the gas constant. That is there. And N sub A is Avogadro's constant, which you probably remember from mole day. But it turns out Boltzmann's constant is just dividing 2 other constants. So the dude got his own constant just for dividing 2 other constants. Good for him. All right, but that's the idea. So it depends on what you're looking for. But either one of these will relate temperature and average kinetic energy for you. So putting it all together, we have had many experiments that were done a couple hundred years ago and have been done many times since to kind of see what happens, how all these things are related. How are pressure and temperature related? How does the volume of the container relate? And so we establish a couple different laws that are the gas laws, and we essentially are going to cram them all together into one equation that many of you will recognize from chemistry class. These gas laws were developed independently through experiment, and we, you control everything that you're not looking at, of course. You have one independent variable, one dependent variable, and you want to see how these different macroscopic quantities are related. For example, the first law that you want to be familiar with is called Boyle's law. And this looks at the relationship between pressure and volume. And it turns out pressure was inversely proportional to volume. This might make kind of logical sense. If you double the volume of, say, a balloon, the pressure would cut in half. If you triple the volume, the pressure cuts down by a factor of 3. Right? You're changing the size of the container, so when we talk about the force on the walls, they're going to necessarily change. There you go. That's Boyle's law. Pressure and volume are inversely proportional. I would get some kind of graph that looks like this. I were to plot pressure versus volume. So as I increase the volume of a container, the pressure goes down. Vice versa. Again, it's important that we control everything else, so we would call this an isothermal system. This works assuming that the temperature is staying the same, because the temperature is another factor that can affect things. The pressure and volume are inversely related. That's Boyle's law. Let's look at some others. Another law was Charles's law, where we looked at the relationship between volume and temperature. And it turns out those 2 things are directly proportional. So this is a nice, easy one. Volume and temperature are directly proportional. Again, assuming that I have the constant mass of gas, kept at constant pressure, which we call isobaric. That'd be constant pressure. So here I get a directly proportional thing. If temperature increases, volume increases. So if a balloon gets warm, it's going to swell in size. If it gets cool, it's going to decrease in size. That's the relationship between volume and temperature. Sometimes this one we just call the third gas law. Poor Mr. Amonton. But this law, you can see we're just looking at different permutations here. So now we look at pressure and temperature. And it turns out those are also directly proportional. Pressure and temperature very much depend on each other. So if the temperature decreases, so will the pressure, and vice versa. This would be isochoric, so you have a constant volume. And again, we would, of course, get a graph that looks like this, directly proportional, straight line through the origin. You double the temperature, the pressure would double, assuming that the container, say, can't change its size. That one hopefully makes sense as well, because high temperature means the gas molecules are flying around at a higher kinetic energy, so they're going faster. The collisions with the wall then would be more frequent and perhaps more violent, and so you'd have a higher pressure. And the last law you want to be familiar with is Avogadro's law, and this one looks at the number of moles. And again, amazingly, another directly proportional relationship. So the more molecules, which is really what the number of moles is measuring, or the more particles, then the higher the pressure. The higher the volume, assuming that we're keeping the pressure constant. So we look at number of moles versus volume. All right, if you need a refresher on the number of moles, this is, of course, something from the good old days in chemistry class. But the number of moles is a way to measure how many particles there are in a realistic or easy to use way with reasonable numbers, because usually you're dealing with ridiculous numbers of particles or molecules. So we use Avogadro's constant. The hard thing about this equation is just remembering what's what, because there's 3 different n's. So n sub a is Avogadro's constant. That's probably the easiest one to remember because it's got the a subscript there. And it's also in the front of the data booklet. They tell you n sub a is the constant, and they give you the number. You know and love it, 6.02 times 10 to the 23 per mole. That's how many particles or molecules or atoms there are in a mole of a substance. So that's the number of things in 1 mole. That's how we define a mole. It's that many things. So it's just because you're dealing with ridiculous numbers that we say, rather than saying you have 12 times 10 to the 23 particles of whatever, CO2, we could just say, yeah, you got about 2 moles. Right? So that's Avogadro's constant. So that would mean then I would essentially set it up like this as a ratio. N is the number of particles, capital N, so little n would be the number of moles. So just as a refresher, if you need it, they do have this in the data booklet for you, which is nice because it's sort of a definition thing. For the number of moles, you just need the number of particles divided by Avogadro's constant. And of course, you can go back and forth between number of moles and number of particles, depending on what the problem gives you, what you might need. All right, so putting it all together, all of these things are proportional or inversely proportional. And when something is proportional, remember, we can do the thing like E times V would be a constant. It turns out all 4 terms I could combine like this, and they would be equal to some constant, which we will call R. That is the ideal gas constant. So here you go. This is we call it the equation of state of an ideal gas, or a lot of times we just call this the ideal gas law. Sometimes we affectionately call it PIVNERT, because the equation is PV equals nRT. P is the pressure of the gas, V is the volume, and the number of moles are the gas constant, which is in the front of your data booklet. There it is. E is the temperature. So all of the different properties of a gas are related to each other. Depending on what you're changing and what you're looking at, will affect what you put in and take out of this equation. But you can see how changing one will affect any other thing. So this you use a lot if there's problems where you're talking about the pressure, volume, or temperature of a gas. That is the equation that you use, which we will practice in the coming days. All right, so there you go. That is pretty much everything you need for the kind of base knowledge on gases, and we will get into it with some simulation and playing in the coming days. Until then, have fun.